Hello and welcome to the next video in the AI series. So our focus this time is going to be taking a look at behaviors. So previously we got set up our navigation system. We were able to have that working in our first-person environment with the Unity Nav Mesh, and also have it working in more of a real-time strategy environment with our custom pathfinding. So with the behaviors we're working on today, we're going to again have those work in both environments, and there won't actually need to be anything that we do different for them. They will actually just work. The navigation system will take care of the differences between the two environments. And what we're going to be setting up is something that's going to use a mixture of goal-oriented action planning, or GOAP, and we're going to set up so that our actions have an easy way of being able to be state machine based, because GOAP and state machines blend together really, really nicely. So we'll set up some stuff to make that really easy for us working with. So here's what we've already got. We've got, as before, our first-person environments, and we've also got our strategy environment. We have also now this debugger window, which is not going to be doing a huge amount at the moment, but it is going to be something that we are adding more things into to make it really easy for being able to have some debugging info for our AIs. And I've kind of already pre-planned a few of the interfaces there we'll be able to see. So we have this AI debugger object that keeps track of the particular AIs, and the window is going to be able to retrieve some extra info and display it, just so it's going to make it a lot easier for us debugging. And I've already set up a couple of goals and actions just as skeleton versions, so they're not doing anything yet, but we've got our general structure here that we're going to be working with. And so I'm going to be making use of, with our base goal and our base action, those will be abstract classes, so that we can enforce certain rules for functions that must exist. So where we're going to begin is with our planner, the Gop Brain. This is going to handle the actual working out what actions and goals are going to be running. So there's different versions of GOAP that you can encounter. The sort of classical versions, a goal is achieved through a chain of actions. So goals have a priority. We pick the highest priority goal that can be achieved. And it's achieved by chaining together individual blocks. So for example, if you were wanting a character to have a goal to satisfy hunger, they need to acquire food. So there could be different actions they pick for that. They could pick one that involves them going and gathering food from outside. They could have one where they go to a storage container. They could order food. You could have different things there. But all of those actions result in, I am now holding food. Then you have another action to consume food. So that version, I'm not going to set that up. It's one that involves a lot more infrastructure. And it's something that until you have quite a large sort of scale and scope of behaviors there, you don't really get much of an advantage to it. And actually the higher implementation cost tends to make it that it's a lot slower to get things up and running. So I prefer a style of GOAP where an action completely satisfies a goal. So goals still have priorities, but it's a one-to-one mapping. So one action entirely completes a goal. We could have multiple actions that complete the same goal, and it picks the one with the lowest cost. But the key thing is that it's one action. That makes our planner simpler, means there's less state we're tracking, and it makes our infrastructure much quicker to get up and running. And like we're talking quite a significant difference. So that's why, unless you've got a large AI setup that you're building, I don't recommend going for that sort of finer grained approach. They'll give you an equivalent result in terms of the behavior that the player experiences. Its main impact is on that development side. So when it's a small number of behaviors, we're going to go for a simpler, quicker setup for implementing things. So how we'll structure these ones is our AI is going to have a Gop Brain. We'll add on the goals. The order here doesn't matter, but this just is a logical order for adding these in. Then we'll add in our actions. So that gives us this, so we can now start setting this up. So the brain needs to work out what is the goal and action that's going to run. So first thing, it needs to get the set of goals and actions it has available to it. So we're going to have base goal, goals, base action, and all of our actions. We're going to, in a wake, populate those. So we want those fully populated. So we're going to goals, we'll get components. And this is one of the handy things with using inheritance. We can just retrieve base goal, and anything that's based off of that, anything that inherits from that, we'll retrieve that into the array, which is really handy. So we do the same thing with our actions. So we'll grab the base actions. So, okay, good. Now we're going to set up our update. So update, if we think about this, goals have priorities. And especially for debug purposes, I really want to be able to query that priority at any point. So we don't want it to be a case where we say, okay, get priority, and it does the calculation every time, because we'll be doing that a lot. We actually want it to have a setup where it refreshes and populates those priorities to begin with. So what I'm going to set up is that these, in the base goal, we have public void, and we're going to call this pre-tick, because that kind of describes what it's actually doing. We'll make that abstract because that's something that we want every goal to do. So the first thing we'll do is pre-tick all of the goals to refresh priority. So that's the goal here. So for, and just because we're looping through these a lot, I'm going to use an integer-based for loop. So we go through all of these. Goal index is less than goals.length. And all we do is we just go, okay, well, goals, goal index, and pre-tick. So the intent of this is for it to calculate priorities, to calculate whether the goal can run. That means we need an accessible thing for being able to access the priorities and whether it can run. So we're going to have a bool can run, publicly gettable, but protected on the set, and we'll default it to no, so it can't run. Same thing for priority. Priority, public get, but a protected set. And we'll go the lower the number, the lower the priority. So we're going to say that if we do nothing, the priority is 0. So we can start to set these priorities up. For idle, what we're going to do is we'll set up our pre-tick. So, okay, well, idle can always run. There's no reason why idle can't run. And its priority, I actually kind of want its priority to tend to always be 0. Because I don't want it to be something that is, it's there as the fallback. So something that I really recommend with AIs is always make sure there is an active thing that they are doing. Even if it's a case where they do nothing, find a way for them to do nothing in a way that is somewhat expressive. That might be that they're making noise, they might be playing some animations, things like that. Don't have them just, stock still, not moving. Have them actually doing something. It makes them feel more alive. If they're just really stock still, it seems like a bug. So, okay, that works for idle. For wander, wander's going to be a little bit more complicated. Because with wander, what I want it to be is every so often, the AI essentially gets the urge to go for a wander. So that means, and after a time of wandering, they're like, nah, I want to chill for a bit. So they want to actually stop. So what I want to do is have something where, okay, wander time, so how long they will attempt to wander for, and then a cooldown, so wander cooldown time. And we might say that, okay, if they've wandered for a bit, they're then going to just chill for a short little time. So, okay, then I need to be knowing if I'm currently wandering. Because if I'm wandering, then I need to be checking how long I've been doing that for. If I'm on cooldown, then I need to be checking that time. So what I want to... So for when I'm wandering, I actually know that pretty reliably in that the goal is only going to be running when they're wandering. So I can go and say that in here, we're going to have public bool is active. And for now, I'm just going to do it like this. There will be some changes we probably make to this afterwards, because we do need to be populating that. But what I will say is F is active. So that means, are we currently wandering? Currently wandering. If we are, then we need to update our time. So float action time. And what we will do is, okay, well, action time plus equals time.delta time. If our action time is less than our wander time, then can run is going to be true. So we can actually just say can run is this. Otherwise, what we're going to be able to say is, so we're doing something other than wandering. In that case, and action time, we can get away with updating that always because we'll use the same timer for wandering versus cooldown. The difference is that here we would say can run is if action time is a greater than the wander cooldown time. And then priority, we're just going to give it a base priority. So int base priority, maybe 25, because we're controlling this not just through priority, but whether that hard locking of whether it can actually run or not. So this will have it that once we hit the wander time, it will no longer be able to run, whereas this one, once we pass the cooldown time, it will be able to update. Now, there would be a potential that this number could get quite large, which could cause issues. So I will actually return back to doing this in this manner, just so that I can add a little bit of a safety check here. So F action time is less than wander cooldown time, then we update it. Just avoids it going to, potentially huge values, which could cause issues. So, okay, this should mean that it wanders for a time. That looks good. We're going to have a need for being able to set that action time, but that's something where we can assume this goal, or any of the goals, are going to have a function that runs when they are started and when they are stopped. So that will be an important thing that we know we need to set up. So that's something where what I would be doing, this is a case where I would have a bit of a mix of something that is virtual, something that is abstract, and is sort of the setup I would go for this potentially, or we can just use straight virtual. So we're going to say that when that goal starts, we're going to call that wake up. Wake up, which it won't actually do anything at this stage. And we'll also have public virtual void go to sleep. Because then in our wander, we're going to override those. So when we wake up, so waking up means that we've started wandering, which that's going to allow us to do a place to do things like picking locations, stuff like that. So first thing, we make sure we run the base one, and then we'll say, well, action time is equal to 0. And then when we go to sleep, it's going to be a similar thing. We run the base one for go to sleep, and we reset the action time to 0. Just means that we're sort of tapping into that life cycle for updating those. So, okay, that's pretty good. We're largely got everything we need there for our goals. They don't need anything too much more than that. There'll be a few little bits that we'll encounter along the way, but that's pretty much the bulk of what they actually need. So we've gone through and done the pre-tick, the setup there on the goals. The next thing is now doing the actual planning. So doing that process of finding what is the highest priority achievable goal and being able to run that. Okay, so to work out which goal to run, first thing we need to do is we need to actually just search through all the goals. But I'm going to put this in another function, refresh plan, just because it's good to sort of split these areas up so that we're avoiding functions getting too long. You really want to avoid having functions get much longer than the length of what you can fit on a screen, ideally. I have encountered and had to work with functions that were thousands and thousands of lines long, and that was not a fun day for anyone. And no one wanted to refactor it because that was terrifying code. So we want to avoid that. So we're going to loop through all the goals. We're going to be keeping track of our base goal, best goal, and base action, best action, because we're searching for the best pair of those. So the best combination of the goal with an action that can satisfy it. So find the best goal action pair. So, okay, we've grabbed a goal here. First thing we want to do is stash this just in a variable, make it easy for ourselves. Just avoids constantly having to do the array lookup, things like that, which can get optimized, but it just means that this is neater code for us as well. So that goal might not be able to run, so we're going to check it. If the candidate goal if it can't run, skip. And also, this goal might be more expensive than a best goal we've already found, in which case, there's no point doing any further work on it because it's never going to get picked. So, if we have a best goal and the best goal's priority is higher than the candidate goal's priority, then we will also skip. So skip if can't run, and we also skip if current best goal is a higher priority. This just avoids us so that because going and checking the action, we're having to loop through every action, so even if it's a quick check, which it is a quick check, still we're doing it a lot of times. So anything we can do to avoid and skip slow checks is good. Gives us better performance just by how we order the code. So these quick little early out ones that are rapid to check, always good to do. So then we now need to find an action that can satisfy this goal. So we're going to stash here. This is going to be best action for candidate goal. And then we're going to loop through all of the actions. So I'll set up with action index. Action index is less than actions. And this then gives us a candidate action. So a candidate action. So the goal is with this is to find the cheapest action that can satisfy this goal. Find the cheapest action for this goal. So what we then do is we need to check here, did we actually find anything? If we found something, then that means we have a new best goal with the corresponding action. So best action. So this means we found a viable action. So that's good. So first thing with the action, we need to check if it's going to be able to actually satisfy the goal. Because if it can't, there's no point doing any other checks with it. So if candidate action can satisfy, and if that can satisfy the candidate goal. So check it. So essentially we're skipping if it can't actually satisfy or if it can't work for that goal. So skip if action cannot satisfy the goal. So that means the action can't achieve it, which makes sense because we'll have things like our idle action is not going to be able to achieve the goal of wander. So really quick check ideally there. And then the final thing is we need to check cost because we might have found a cheaper action for solving the same problem. So is this action more expensive? F, so skip. So F, we have a current viable action candidate and the candidate action, if its cost, we don't have that function yet, but we will. So if its cost is greater than our current cost, then we skip. Otherwise, we'll be able to actually say, yep, this is a viable option. So that means we need our can satisfy and cost functions, so we can set those up. So can satisfy, that's a thing that we're going to make abstract because every action must implement this. So can satisfy base goal, goal. And we also need that cost function. And again, we're going to make it that every child class must implement this because it's something that is very core to it. So, okay, those become an override. So for whether it can satisfy the goal, that's actually a pretty easy check. So return goal is the idle goal. Cost is a bit of a trickier one. So with cost, what we find with that is for idle, it doesn't really have a cost. So I'm just going to make it 0. Cost would more come in, there are a way for it to distinguish between which of multiple actions that achieve a goal should run. So it's something that we want to have the infrastructure there for needing it in future, but it's something where at the moment these costs don't actually have much meaning because we don't have multiple actions that can satisfy wander. We don't have multiple that can satisfy idle. But we want to have that infrastructure there because it's going to be really important for us once we do start scaling things up. So, okay, that's the majority of the planning. We've got the majority of the planning there. Now, at the end of this, we need to resolve what we do. So we've refreshed the plan. We have a best goal and a best action. So there's a number of possible scenarios. First scenario, the goal and action are exactly what we're already doing. So in that case, if best goal is equal to active goal, which we need to make sure we're tracking that. So we're going to have base goal, active goal, base action, active action. So if the goal is exactly the same and the action is the exact same, we don't need to do anything. because all we've done is essentially we've confirmed that this current plan is still a viable course. So if the best action and best goal are the same as the current ones, do nothing. So the current plan holds, do nothing. So that's one scenario. The other scenario we could hit into is that the best goal is null. Now that generally shouldn't happen because we should be setting up fallback actions like an idle that it will always pick, but say it did happen. That means whatever was running needs to stop. So we're going to check if best goal is equal to null. Then we're going to say, okay, did we already have a goal? If we didn't have an active goal, or if we do have an active goal, we need to shut things down. So we need to be able to say, okay, well, active goal, go to sleep. It doesn't need to be running anymore. And then we're going to null these out. So active action is null, and we just do a return. So no plan viable currently. So that's good. We're detecting if the plan is unchanged or if there is now no viable plan. So the remaining alternatives that we have is we could have a different goal to what we've currently got. So we've changed priorities of what we're trying to achieve. Or we could have a different action for the same goal. So we need to do a little bit in terms of checks here just to make sure that we're handling things correctly. So we have our two scenarios of we could be keeping the same goal but changing the action, or we could be an entirely different goal. So we're going to handle if we've got a different goal first. So if best goal is not equal to active goal, and the active goal is not equal to null, then we need to tell that active goal to go to sleep, which we will do the check actually identical to this, and we'll do it inside the loop here. The reason being is that if the goal's changed, we then also still need to say, well, okay, the best goal has to wake up. So we put the previous goal to sleep. So goal has changed. We put the previous one to sleep if we had one. Then we wake up the current one. Then what we're going to do is say, okay, well, best goal, set the action to best action. And we're going to update our key variables. So active goal is equal to best goal, and active action is equal to best action. And I might actually change these around just order-wise. I think it reads better. So start the action. So it's good. We've got the life cycle stuff there telling goals to go to sleep, wake up. That means we can in wake up is active is true. In go to sleep is active is false. And we make sure that in our goals that might be overriding that, we're definitely calling the base versions, which is good. The other thing that we know we need here is that set action, because goals do need to know about the action that's running. So we're going to have public void set action, base action, new action, and this one doesn't need to be overridden. But we will have protected base action, linked action. And we will update that here like this. So when we go to sleep, we want to actually stop the action. So we're going to say linked action, go to sleep. Or maybe halt might be a better term for it in this case, because the goals are always there and are always sort of, alternating between awake and asleep depending on priority, but the actions, it should be more treated as more of a stop. So when we set an action though, then it can begin. So that gives us a couple of other functions we know we need. So our base action is going to need a public abstract void begin and a public abstract void halt. So these will just run when they get started and stopped. So that means in our wander action, we just set these up. We won't be doing anything in them yet. It's more just about having these actually ready for us being able to use. So that looks good. Got our key functions. So where we're at now, we've got our structure for our goals. They have priorities, whether they can run. We're updating those. We're going through those to determine what we're wanting to run planning wise. So we're finding the best pair of goals and actions. So the highest priority goal with the cheapest action. And then we're doing a couple of checks just to see, are we changing plan, things like that. So we've got that up and running. That's good. We have enough that we can connect this to our AI debugger now. Even though our actions are not doing anything, we can connect it to the debugger. So I'm going to, in start, say, okay, well, AI debugger instance, if we have that, then AI debugger instance register this, and then a similar thing in an on destroy, just to deregister. So on destroy, deregister, and we also then, I kind of defined the interfaces I wanted for this earlier. So we're going to uncomment this code out and see the bits that it gets grumpy at. So the brain needs to provide a couple of little helper functions here, and that's fine. So we'll set up public string active goal. So this just needs to provide the name of the active goal if we have one. So if active goal is not equal to null, then we get the type of the active goal, which we might not be able to do there. We can instead do active goal get type name, otherwise none. We know we need the same thing for the active action. So we'll just set that up as well. Just means that we've got those bits of info coming through. And then finally, we need to be able to retrieve the number of goals and a little bit of debug info for them. So num goals is easy because we can just link that to goals length. The getting of the debug info for a goal is a little bit more involved. Not too much more though. It's going to be this. We provide the index for a goal. And then all it needs to do is, for that goal, what we want to return is the name of it. So, okay, that's straightforward. Goal, just to make it easier, less sort of long-winded version of what we're having to write here. So goal, get type, name. So we can output the name of it. And then we can say priority is equal. We can just go goal priority, and run, and run. And we just return that. So that'll feed into our debugger. So we should, with our debugger, with this setup, be able to actually see these behaviors changing. We're not doing anything with the goals at the moment, but it should be enough that we can see state information changing. So we'll bring up our debugger window and run this. And we can see our character appears here. So the active goal is currently idle. The active action is idle as well. You can see wander currently cannot run. And that's something where we would expect that wander, and we can see wander changed now that it can run, which is what we would expect. After a short time, it's now able to run. And we would expect then after, again, a bit more time, that can run changes to false, because what should be happening in the background is that can run, those timers and so forth associated with it get updated. And we can see can run went to false. It did rapidly flip back, so there might be a couple of things we need to tweak and sort out there, but that's part of the reason why we have that debug window, so that we can identify things like of this. And once we've refreshed the plans, we now need to tick the goals. So we're nearly at the stage where we've got our behaviors running, which is great. So we're going to check, well, do I have an active goal? If I have an active goal, then I want to tell it to tick. So I want the tick to be handled by the goal, and I'm going to set this up here. Pre-tick is there, so I think it would make most sense to have tick here. Not making it virtual because I'm not intending for this to be overridden. And this is going to go, well, linked action, tick. Again, I use tick for when it's something that I'm causing the updating to happen manually in my code. I try and avoid update to avoid confusion. So in this case, actions, I'm going to make tick an abstract function there for it, because I want to, tick is something where for a goal, goals are likely not going to do anything in tick. They generally shouldn't, but actions must. We expect them to be doing things. So that's the reason for the difference there. So tick, that's fine for idle. Idle literally doesn't need to do anything else. Wander will be doing other things. So, okay, that's pretty good there in terms of that setup. Means we've got everything passing through with our goals. There might be a couple of other little bits we need to add in there, but generally that setup is looking fairly good. Now we did notice that there was some odd behavior with our wander goal in terms of what was sort of happening there priority wise. So that's something where we could have a setup for displaying some extra information could be useful. So now that we have our planning happening, we know the selection of actions, things like if that is working, we've got our debug info there. What we want to do is get our wander action actually happening. So this is one where I'm going to set it up to be able to be supported for our state machine based setup. So what I'm actually going to do is I am going to add in a base FSM action, because not every action needs the FSM setup. Like idle doesn't really need that. Wander does, because wander we need to be selecting location, heading to it. So we've got a bit of a cycle there. So wander is a good example of where we can set this up. So what I'm going to do is, alongside this, we will have base FSM action that we'll just put base action it inherits from, clear out all of those for now. And wander is going to be inheriting from that. So when I'm doing changes like that, I usually create the file, jump back to Unity so it refreshes projects, things like that. So we've got the code compiling. So how I want these FSM actions to work is I want this to be a really quick and easy setup in terms of I want this to be something that is really straightforward for us being able to expand and add to. So I'm going to make it that this base FSM action is actually a generic, and it has then within it protected T state, because we might want to allow the child ones to at least look at that, but we may not want them to actually set it. So this might be one where I go for protected get, but private set. So it'll inherit from that. So, okay, the state can only be controlled within our logic, which is intentional. I need to then keep track of the states. What I'm going to do is have a class here, state config. Again, not making it protected because this is information that things like the wander action doesn't get to see. So this I'm going to have, and I'll bring in using system, because I can actually just set up a couple of things for being able to link to functions, because we know key stuff that a state machine is going to have. We're going to have an action for on enter for when we start that state. We're going to have an action for updating that state. So an on tick. We know we're going to have an action for on exit. And then we know we might need, we know we will need a way for being able to transition to another state. So that needs to be a func because it returns a value. So func t check transition. So that's the config for a state. I can store all of those in a dictionary. So I'm going to have a dictionary. Uses t, so t is going to represent our state. It's actually going to be an enum. So dictionary t state config state machine, and we'll initialize all of that. So we've got that set up, which is good. So okay, we need a way to add states to it. So we're going to have a protected void add state. We need to provide the identifier for it. We need to be able to provide our functions. But I'm going to make it that all of these are actually optional so that it doesn't have to actually run them. So on enter function, which will be able to be null. We'll have an on exit function, also null. And I'll organize these like this just so it looks a little bit neater, make it a little bit easier to read. So on tick functions, the idea is that if you don't provide a function for this, it will substitute in a default one. It makes it a little bit more flexible for people structuring the code here, and that's really the goal. These also don't need to do system dot because I'm using system. I'm just very used to not having to, or having to do the using. So we then want a func t check transition function. Also able to not be provided. So that's good. We've got those. Then adding in the state really doesn't take much. State machine, the state that's been provided equals a new state config, and then I can just initialize this like this on enter. It's equal to our on enter function. On tick is the on tick function. Can set up on exit. Really quick, easy way for initializing stuff with the structures. Saves you having to do make a constructor for it. Get transition function. Done. So that adds things into our state machine. So our state machine then needs to tick. So we're going to, if we remember, base action could override tick. So we're going to have public override void tick. And we are also going to make this sealed because anything that's based off of FSM action, we don't want it to be able to provide its own tick. We want to have it that we are fully controlling that within this FSM action, and then the child ones that inherit from that, they have to use these appropriate state functions. That's going to make it a little bit more reliable in terms of the structure for it, avoids people potentially doing things that might cause problems. So, a couple of other little things I'm going to do to make my life a little bit easier is we're going to have our versions of these that are the default. So on enter, and this is ones where if we want, we can just then, so it allows us to either have a specific function for the on enter or a catch-all one, which is going to be handy. We have a protected virtual void on tick. Same thing for each of the different ones, protected virtual void on exit. So it gives us stuff we can override, but not stuff that we're required to. And then same thing for the check transition. That will return our type that we've provided. So check transition, and that's just going to, the default behavior will be to just return the current state, so not to make any changes. So, okay, that's good. What we can then do is in tick, well, first thing, we need to tick the current state. So we need to set up our tick function, and that means at the moment we need to check if our on enter ones, for example, are null and run the corresponding one. With a little bit of a change here, we can make it really easy on ourselves and make our code later on simpler. So it's a small little extra bit here, but it makes a big difference. So we'd say on enter function, if that is not equal to null, then we use on enter function. Otherwise, we use on enter, which is going to refer to our one down here. We can then use similar logic for each of these. So we check on tick function, on exit, and that way it's going to make it really easy for us actually running these. So check transition, again, is that not equal to null. If it's not null, then we use the one that's been provided. Otherwise, we use the built-in one. So what this means is down here, I can just go, well, state machine, state, on tick. So we tick the current state. Then we need to check for transitions. So we would say next state, state machine, state, check transition. So when we're checking for the transition, one of the first things we want to do is check if we're trying to transition to the exact same state we're already in. Now that is actually going to be a little tricky, because if we do next state equal to state, it's not going to work because we're working with generics. So the way we have to do this is a little bit different. So we actually have to do a quality comparer, provide our type, default equals, and then we provide state and next state. So if we're transitioning to the same state, then we just do return. Otherwise, we now know we have a state transition happening. So that means we can say, okay, well, state machine at the current state on exit, we can change the state to the new one. And then we would say state machine for that new state on enter. So form the transition. That also means at the very beginning, we need to run and do our actual initialization of entering whatever state we're currently in. So we'll get the states being populated in Wander first. So what I would have here is enum, public enum estate. So in terms of the states that we've got for this, if we think about it, the Wander needs to be finding a location, following it, and then that's sort of the key states it's going to do. So we've got finding location, moving to location. So we would say base FSM action, and then action wander eState. So good so far. We get rid of our tick. We need to do some setup though. We need to actually create those individual states there. So we're going to set up here a void start, and we're going to have public abstract. It doesn't need to be public, it can be protected. So a protected abstract void initialize, which we will run here. And so this, our FSM action doesn't need to implement it, idle does. It's not going to do anything in idle, but it does need to have that function. In wander, however, what it's going to do is it is going to add state, eState, finding location, add state, eState, move to location. So we've created our states here and we're ready to start getting those populated in terms of what they're doing. There's a little bit of housekeeping we have to do first with this. So first thing we need to do is be able to actually start in a particular state. So that's easy enough. We're going to have protected, and we'll mark this as a serialize field, T initial state. And we already have our begin functions that run. So we already have this begin and halt that exists there. So what I can do is over an FSM action, those are probably things that the child class, I don't actually want them implementing because we've already got state transitions. So we're actually going to grab those and seal them so that everything has to go through our state transition functions. So in the begin, that's fine. We'll be able to go state is equal to initial state, and we'll be able to tell it to enter. So we'll be able to say state machine, state on enter. So we're reliably in our begin, properly setting things up. Halt, which we know that halt runs when something has been stopped. So with our goal, when it goes to sleep, it stops the action. So what we would do here is state machine, whatever that current state is, exit. So we've just got a little bit of life cycle stuff happening there. Now our wander action is going to need to work with our navigation system. So we're also going to here, just so we've got easy access to it, retrieve that. And we're going to retrieve that in an awake, just so we've got it right from the very beginning. So we're just going to say navigation, get component. So that's good. We've got our navigation system retrieved. We can start to fill these out. So first thing, we know we're going to need to be able to pick a location. That's the thing we know we need to have to do. So I want to be able to control the range that it wanders. So I want to have a min wander range. Maybe we'll make that 25 meters. I want to have a max wander range. So the max wander range is going to be, let's say, 50. So I need an ability to pick a location. So void pick location. So first thing I'm going to do is pick a random direction and distance. So pick a random direction and distance. So that's quite straightforward. Angle, we're going to work in radians. The reason there being that we're using, in a moment, sine and cosine. So it's easier to be already in radians for those because that's what they use. We'll pick our distance. So it's going to be a random range between our min and max values. So min and max wander range. Now, generating our wander position is not too involved. We start by using our current location. Then we take that and add to the x distance by mathf sine of the angle. And then on the z, we just use cos. That will give us something that is whatever distance we have selected away and at a particular angle. So this, we're generating a position, but it might not be valid. We need to actually ask the navigation system if that's valid. So we can go, hey, if navigation, find the nearest point. Here's the wander position. It needs a search range because the location might not be valid, but it might be able to find one nearby. So a search range of 5. So we give it the search range and then we just output to that. So now we know we have found a valid wander position. So I'm going to have a Boolean here as wander pos, which will default to false. And we will set that here to true. And we'll actually vector 3 wander position, or wander target is a good name for that. So, okay, we're finding the nearest valid point. So let's think about how this needs to work state-wise. When we enter finding location, we want to try and pick one. It could fail to find one, in which case we want to repick. So we've got two different setups there for it. In enter, there's definitely stuff we need to do. In tick, there might be stuff we need to do. And we also need to check in our transition if we actually found a valid spot, because we should only transition when it's actually got a valid location to head towards. So that means we're going to need an on enter for finding location. We definitely need an on tick for finding location. We don't need an on exit, but we do need a check transition. So there's a few little functions we need to set up, but these are pretty straightforward ones. Because when we enter it, well, it has wander pos. We're going to set that to false and do a pick location. The tick, also really straightforward. Tick is just going to say, well, if we don't have a wander pos, pick the location. And even the check transition doesn't need to do much. So it returns the state, check the transition, and it's just going to be a case of, if we've got the wander pos, then our state becomes moved to, otherwise we just stay in finding location. So that's it for our first state. We just need to add those three functions. So that's good. So moving to the location, when we enter it, we want to tell the navigation system to head towards that. So we're going to need an on enter. So move to location. For the tick, likely not anything we need to do. Same for exit. Check transition though, definitely going to be stuff we need to do. So check transition, move to location. So let's set these up. On enter, doesn't need to do too much. It would go and say, well, navigation, set destination. And it's going to give it that wander target. Now, this could fail. So if this fails, I'm going to set wanderpos, that we have it, to false. Because then in our check transition, I can look for stuff like that. So I can say in the check transition, well, if for whatever reason we no longer have a wander position, then we need to find one. There's a couple of other cases where we might need to do that. If it is not at that destination, then it needs to be trying to move towards it. So we could check, well, or even if it is at the destination, really if it's anything other than trying to find the path, it needs to go to finding location. So we would be able to say, if it doesn't have a wander position or navigation is not finding or following the path, then we need to find one. Otherwise, state is moved to location. So if it doesn't have a wander position, or we're not finding or following the path, we can also check, are we at the destination? Is at the destination, then we need to pick a new one. So those are the key criteria, that it doesn't have a wander position, which could happen because something failed in terms of the path finding. We can also, you might have gotten interrupted, might no longer be at the destination, or might now be at the destination. So we pick a new location. So that's pretty good. If it's already moving and this goal gets interrupted, we actually do want an on exit so that it can stop moving. We need to cancel the movement. So on exit, move to location, and it doesn't need to do much. It's fairly straightforward, but what it is going to do is tell the navigation system that we're not moving anymore. So we can tell it to stop movement. So now we've got our state machine set up. So we made specific use of things like of sealed to ensure the order that stuff's running in. So let's test this out. We should expect to see that it's actually still moving. It gets to locations and then picks a new one. We'll be able to see info in the debugger window. So we'll notice it's not currently moving yet, which is correct because it's in idle. It's now going to be in wander, heads over towards its location, picks another one. So it's properly moving between the different states, which is good. When it changes to idle, which it will not do for a little bit, it should also then cancel any current movement if there was any left over at that point. But that's working quite nicely. And so it stopped, so it's back in idle. We can see that information there, which is good. Then it started back after the timeout. Now, we're going to go to our procgen terrain. And we're going to go to our enemy here. And I'm going to add in the Gop Brain. Going to add in idle and wander. And the actions as well. And then I'm just going to hit go. Because this doesn't have its move target. We've turned off any of the sort of debug bits intentionally. So now we can just run this. And let's see what happens. What should happen is it wanders. We've got our debugger window. We can see the states there. And it starts wandering. With no changes to the behaviors, we have a behavior that works in two very, very different environments. In one case, an environment where it's using the Unity nav mesh and it's having to, it's handling a lot of the movement, and in another environment where it's our own custom pathfinding. And our behavior code didn't change. And that's the goal. That's the reason for that navigation layer, is so that it abstracts those differences for us. And so we've now got our setups. We've got our FSM actions for if we're needing something that has a bit more staging to it. And we've got a reasonably clean interface for adding those states. We can set up very tailored, targeted functions for enter, tick, exit, transition for a particular state. We could also set up more monolithic ones if we wanted, and those will automatically get run as a fallback. We also just have our very simple base action for if we just need something that is going to do very simple logic, so things like our idle. So it allows us to handle both sides of things. And we've got a bit of a debugger setup that makes it easy for us to see information, so we can see what's sort of happening there in the game, get a bit of an insight into what the AIs are thinking and doing, which is ideal. That makes it a lot easier for us working with them. So this is going to give us a good base for then we're going to be adding and extending onto this. We're going to be building up more complexity in some of the behaviors in some of the other systems for this as we expand out our AI, with the key goal that essentially everything above navigation is not going to care whether it's running in that first-person environment or the other extreme of that more sort of a real-time strategy environment. That's the intent, that it works regardless, and our behaviors just work because of the systems and structures that we've put together. Thanks, folks. I hope you found the video helpful. If you have, chuck in a like and subscribe, really helps out. If you're looking for the code for the project, then there's a link to that in the description below. What I'm doing with this is each part of the series is getting tagged in GitHub, so you'll be able to go direct to the code as it was in the particular video. And if you've got any questions, chuck in a comment below, or if you want, chuck them in for the next Q&A video. And if you're looking for other ways to support the channel, I do have a Patreon, and the link to that's in the description below. But until next time, bye.